Welcome back, everybody. In this section we're going to look at the various number systems that we can use for arithmetic. We'll start with the familiar decimal system and also look at the binary, octal, and hexadecimal systems. So of course you're familiar with the decimal system. What digits does the decimal system use? It's tempting to say that we use the digits 1 through 10, but of course that's not true. 10 isn't a digit. 10 is actually 2 digits. So we don't use the digits 1 through 10. We need to have the number 0 to represent 0, and so the decimal system uses the digits 0 through 9. Anything beyond 9 requires more than one decimal place. So if you take a number like 6038.415 in the decimal system, we can always clearly indicate what system we're using by putting a little subscript. That subscript of 10 tells us that that number is representing a base 10 number. So one of the first things you need to know how to do in order to understand the way that these number systems works is to be able to write a number in expanded form. You know when you read this number that that 6 means we have 6 thousands. And this is the thousands place because that is our base of 10 raised to the third power. We have 0 hundreds in this place, or 0 times 10 to the second power. We have 30 represented by that 3. That's because that is the tens place. 8 is the ones place. And the way that this becomes a 1 place is that that is 10 to the 0th power, because 10 to the 0th power is 1. So we have what you're familiar with: the ones place, the tens place, the hundreds place, the thousands place, and so on. Then we have our decimal point, which is the dividing place between whole numbers and parts of a whole. The first place to the right is the 10 to the negative 1, or tenths place. So we have 4 tenths. Our 10 to the negative 2 place, the next lowest power of 10, represents 0.01, and we have 1 of those. And of course our thousandths place is 10 to the negative third, or 0.001, and we have 5 of those. So to write that number in expanded form, we're going to use a lot of parentheses here. We have 6 times 10 to the third, plus, we don't have any 10 to the second power, but we do have 3 times 10 to the first power. And then we have 8 ones, or 10 to the 0 powers. And then we'd have our decimal point, where we'll add on our parts of a whole. We have 4 times 10 to the negative 1 power, 1 hundredth, or 10 to the negative 2 power, and finally we have 5 thousandths, or 10 to the negative third power. And so each place represents a value, and that's what we call the number when written in expanded form. So you take just a minute and write the number 62,008.25 base 10, or decimal, in expanded form. Unpause the video when you're ready to see the solution to that. Okay, let's take a look. The 8's place, or excuse me, the 8 is in the ones place. That's 10 to the 0, 10 to the 1, 10 to the 2. Our 2 is in the thousands place, or the 10 to the third place. And the 6 is in the 10 thousandths, or 10 to the fourth place. Our 0.2 is the 10 to the negative 1, or tenths place, and the 5 is the hundredths, or 10 to the negative seconds place. So writing that number in expanded form, we have 6 10 to the fourths, 2 10 to the thirds, no 10 to the seconds, no 10 to the firsts, but we do have 8 ones, or 10 to the 0. And there's our number in expanded form. Be careful here. This is the easy place to make a mistake. A lot of times it's tempting to say that that 8 is the 10 to the ones place because it's the first digit. But again, since that's a 1, it has to be 10 to the 0 power, which is equal to the 1, or the ones place. So here's a question. What is the biggest 6-digit decimal number you can have? Well, since we're limited to 6 digits and we want it to be as large as possible, that must be a set of 6 nines. 999,999 base 10. Any number bigger than that, namely 1 million, would roll us into a 7th decimal place. But a little bit tougher, what is the smallest 6-digit number you can have? Well, it's tempting, but wrong, to say that that would be a set of 6 zeros. In fact, that's not a 6-digit decimal number. You could say that that's equal to 0, and so there's no need for 6 digits. So it's not a set of 6 zeros. We have to have some reason to have that 6th place, and so that must need to be our smallest non-zero digit, which would be a 1, and the rest of the digits could be zeros. And so the smallest 6-digit decimal number we can have is 100,000. Anything smaller than that, which would be 99,999, would only be a 5-digit decimal number. Okay, so let's see how that concept transfers to a binary system. As you probably know, the binary system is a little bit simpler. It only uses 2 digits. We still have to have a digit for 0, and we have to have a non-zero digit, which is 1, and there are our 2 digits in the binary system. So all of our digits are 1s or 0s. So consider the number 101,001.101. No longer do these digits represent powers of 10, they now represent powers of 2. Our 1's place is 2 to the 0 power. What we used to call our 10's place is now our 2's place. Our 100's place becomes 2 to the 2nd, or our 4's place. 2 to the 3rd is the 8's place. 2 to the 4th is our 16's place. 2 to the 5th is our 32nd's place, and so on. And so if we expand the left half of this number, we have 1 times 2 to the 5th. We don't have any 2 to the 4ths, but we do have 1 2 to the 3rd. We don't have any 2 to the 2nd power, or 2 to the 1st power, but we do have 1 2 to the 0th power. And then we get to our binary point. We often call that a decimal point, but since this is a binary number, it's our binary point. Now, in 2 to the negative 1 power is 1 over 2, or this is the 1/2 place. 2 to the negative 2 power, that's 1 over 2 squared, which means this is the 1/4 place. And we could certainly write the decimal equivalent of those as well. If we were turning that into a decimal number, we'll do that in just a minute. 2 to the negative 3rd, that's 1 over 2 to the 3rd. That means this is the 1/8 place. And so if we expand the right side of this number, we have 1 2 to the negative 1 power. We don't have any 2 to the negative 2 power, but we do have 1 2 to the negative 3rd power. And we've written that binary number in expanded form. Okay, you take a minute and write the number 1101.011 in expanded form, and unpause when you're ready to see the solution. Okay, it's always a good idea to start with your 1's place. That is 2 to the 0 power. That means our 0 is in 2 to the 1st power, the 2's place, 2 to the 2nd power, or the 4's place, and 2 to the 3rd power, which is our 8's place. This 0 is in the 2 to the negative 1 power, or the 1/2 place. That's our 4th place, and this is our 8ths, or 2 to the negative 3rds place. So if we expand that, we have a 2 to the 3rd, we have a 2 to the 2nd, we don't have any 2 to the 1st, but we do have a 2 to the 0, or just a 1. Beyond our binary point, we have no 2 to the negative 1 powers. Oops, I'm going to have to drop down a little bit here. And we have 1 2 to the negative 3rd power. And we've written that number in expanded form. So in similar fashion, think what would be the largest 6-digit binary number? Well, we want to use 6 digits, and we want it to be as big as possible. So the largest 6-digit binary number would have to be a set of 6 ones. 111, 111, and that would be base 2. What would the smallest 6-digit number be? Well, again, in order to require 6 digits, that largest digit must be non-zero, otherwise it wouldn't be necessary. So we'll have to start with a 1, and then we can follow that with a bunch of zeros. So that's actually almost the same answer as the question in the previous base. That was the similar question in the decimal system, but this would be base 2 and have a completely different number value. So it's 100,000, but that is not equal to 100,000. So before we move on, let's look at a couple other aspects of the binary system. Which number is bigger, 101, 1101, or 110000? Well, you'll notice that both of these are occupying 7 digits. And just like with the decimal system, the biggest digit values are on the left. The largest place values are on the left end of the number. So the numbers match in their first digits. The number on the left has a 0 in the second digit. This one has a 1. And just like the decimal system, this 1 actually has a greater value than all of these other ones in the number on the left combined. So 1000000 is going to be bigger than 011101. And so which of the numbers is the bigger one? The number on the right is the larger number because it has a 1 in the second binary place, whereas the number on the left has a 0 in that place. So, which of these two is smaller? Take a minute and look at those two numbers and determine which one is the smaller one. Well, again, these numbers are similar. They both start with a 1 in the halves place. The number on the left has a 0 in the quarters place. That means it's the remaining part of that number is smaller than a quarter, whereas this number has a 1 in that place. So this number is going to be the bigger of the two. The question is which one was smaller? By virtue of that 0 in the second place compared to the 1, the number on the left is smaller. Okay, so now that we know what the place values are, let's write a couple of numbers in decimal form, figure out what their decimal equivalents are. We'll be doing a lot more of this in the next section, but we'll get our toes wet here. 11010 base 2. If we expand that, we would say that that is 1 times 2 to the, what power is that? Our first place is 2 to the 0, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. So that's 1 times 2 to the fourth. Plus we have 1 times 2 to the third. We have 0 times 2 to the second. But we do have 1, 2 to the first. And then we have 0, 2 to the 0th power. And so this number is a 2 to the 4th power, 1 2 to the 3rd power, and 1 2 to the 1st power added together. 1 times 2 to the 4th is 16. 1 times 2 to the 3rd is 8. And 1 times 2 to the 1st is 2. And so if you add these two numbers together, they have a total value of 26. And so this number is 26 base 10. Take a minute and see if you can write 101.100.1101 in decimal form. Unpause the video to see the solution. Okay, let's expand this number. Starting over here, we have 1 2 to the 5th. We have no 2 to the 4th power, but we do have a 2 to the 3rd. We have a 2 to the 2nd. And we have no 2 to the 1st, and we have no 2 to the 0th power. Continuing on past our binary point, I'll do that in green. We have 1 2 to the negative 1. We have 1 2 to the negative 2. We don't have any 2 to the negative 3rd power, but we do have 1 2 to the negative 4th power. Okay, so what are the actual decimal equivalents of these 6 binary places? Our 2 to the 5th is worth 32. Our 2 to the third is worth 8. 2 to the second is worth 4. And then beyond our binary point, we have a 2 to the negative 1, that's a half, or 0.5. We have a 2 to the negative 2, or a quarter, which is 0.25. And we have a 2 to the negative fourth, which is a 16th place, which is 0.0625. So if we add all those together, our whole number part becomes 44. The blue part on the left, 32 plus 8 plus 4, makes 44 point. And if we add up the 0.5, the 0.25, and the 0.0625, we get 0.8125. So in decimal form, that becomes 44.8125. Following that same basic idea, we can use really any number base we want. But we're only going to explore the octal and hexadecimal systems because other number systems like base 7 or base 5, while they exist, don't provide a lot of practical application. So 4305.1607 base 8, we can write that in expanded form. Of course, we should explore what digits do we have access to using the octal system. Of course, we're going to start with 0. And since we only have access to 8, we can't go up to 8. Since we start with 0, that would have been a 9th digit. The only digits we have access to are 0 through 7. There is no digit 8 in the octal system, nor is there a digit 9 in the octal system. So let's expand this number. Again, if we start in our ones place, 8 to the 0 is 1. 8 to the first power, this would be our 8's place. 8 to the second makes us our 64th place. We used to call that the hundreds place in base 10. And 8 to the third is 512. So if we expand this, we would have 4 times 8 to the third, 3 times 8 to the second. There are no 8 to the first power in this number. There is 5 ones, or 8 to the 0th powers. And then we have what we sometimes are tempted to call a decimal point, but since this is base 8, it's an octal point. We'll add on our parts of a whole. 8 to the negative 1, that makes this the 1 over 8, or 8th place, and we have 1 of those. 8 to the negative 2 is 1 over 8 to the second. That makes this the 64th place, and we have 6 of those. Our 8 to the negative thirds place, that makes this the 1/512th place. And 8 to the negative fourth, we don't have any of those, by the way. And we do have 8 to the 7, 8 to the negative fourths, which is the 1 over 4096th place. And we've expanded that octal number. So take a minute and write the number 770.137 base 8 in expanded form. In a minute, we'll take a look at the solution. Okay, we have a 0 in the 8 to the 0th, or 1's place, a 7 in the 8 to the first, and then another 7 in the 8 to the second's place. So we have 7, 8 to the seconds, 7, 8 to the firsts. We have no 8 to the 0th powers. We have 1, 8 to the negative 1 power. We have 3, 8 to the negative 2 power, and 7, 8 to the negative third power. And we have our number expanded. So here's an interesting practice problem. See if you can write the first 25 integers using base 8, or using the octal system. We'll do a few together, and then I'll turn you loose to write a few on your own. The first few digits are easy. 1 base 10 is the same as 1 base 8. 2 base 10 is 2 base 8, and so on. So what number will be our last digit where the two numbers are the same in both systems? Well, 7 is the last digit, in which case the representations are the same. Once we hit 8, now we'll require 1 in our 8's place and a 0 after that in our 1's place. And so 8 base 10 is 10 base 8. Remember, there is no digit 8 in the octal system. Now our 1's place will start increasing. 9 is 1 base 8. That is to say 9 consists of an 8 and a 1. And so on. Okay, you take a minute and see if you can fill out the remaining 25 integers in the octal system. Resume the video to see the solution. Okay, as we continue on, 13 base 10 becomes 15 base 8. That's an 8 and a 5 makes 13. 14 is 16 base 8. 15 is 17 base 8. And again, we've hit a 7. That's the highest digit possible, and so we're going to have to roll in and add on another 8. And this means that 16 base 10 is 20 base 8. There's 2 8s and no 1s. 17 is 21 base 8, and so on. When we hit 23, which is 27 base 8, again, we've hit a 7. We have to roll over. 24 base 10. 24 is 3 times 8. No additional 1s. 30 base 8. And 25 base 10 is 3 8s and a 1, or 31 base 8. Okay, we're going to wrap this up with an exploration of the hexadecimal or the hex number system. So which digits does this system use? This creates an interesting problem because hexadecimal, or 16, is a larger base than just decimal, which means we need more digits, not fewer. So we're still going to use the digits 0 through 9, but that's only 10 digits. We need 6 more, and so we also use the first 6 letters of the alphabet, always capitalized. A, B, C, D, and F, where those letters represent base 10 numbers. A in base 16 actually represents 10. B represents 11, C represents 12, and so on. We go all the way up through F, which represents 15, and that's the last digit we need. Again, in a base 16 system, 15 will be our largest digit. When we hit 16, we'll need 2 decimal places for that. So we have some crazy looking numbers. AB03.10D base 16 is actually a number. Let's write that in expanded form. Now there's a couple different ways that we could do this. One way is to treat the A as a digit on its own, which is what I'm going to do, but I'll show you an alternative that's also reasonable. So as we start to the left of our hexamal point, or hexadecimal point, we have 16 to the 0, that's our 1's place. 16 to the first is our 16's place. 16 squared is our 256th place. And 16 to the third is our 4096th place. So if we expand that, we have A 16 to the thirds. We have B 16 to the seconds. We don't have any 16 to the first. There's a 0 there. But we do have 3 16 to the zeros, or 1s. Then after our hexadecimal point, we have parts of a whole. 16 to the negative 1, that is the 1/16th place. 16 to the negative 2, that's 1 over 16 squared, or 1 over 256th place. 16 to the negative third, that's our 4096th place. And our last place is 1 over 16 to the fourth, which is 1 over 20-something thousand. We'd ask a calculator if we really wanted to know. So if we expand that out, we have 1 16 to the negative 1. We don't have any 16 to the negative 2. We have D, which really is 13, 16 to the negative thirds, and we have no 16 to the negative fourth, thank goodness. And we've got the number expanded. Now it would be reasonable to replace the A and the B and the D with their base 10 equivalents. So we could also say that that is 10 times 16 to the third plus 11 times 16 squared, and so on, replacing the a, b, and the d, but either would be acceptable. We'll go with, I like to just use the a, b, and c, and d, so we'll stop right there. Okay, let's wrap this up. You take a minute and expand 3D0.40D2 in expanded form, and unpause the video to see the solution. Okay, the 3D0 part of that becomes 3 16 squareds and d 16 to the first. There are no 16 to the 0. And then beyond our hexadecimal point, we have 4 16 to the negative 1s. We have 0 16 to the negative 2s. We have d 16 to the negative 3s. And we have 2 16 to the negative 4th powers. And we could convert that into decimal by figuring out what all those are on our calculator. We'll do that in the next section. Okay, another practice problem before we bring this section to a close. See if you can write these hexadecimal numbers in decimal form. That's what we're going to be focusing on in the next section. Okay, the first one, EE base 16. That means we have E times 16 to the first, and we have an e in the ones place, which would be 16 to the 0. Since e is equivalent to 14 base 10, we would say that that is 14 times 16, or 14 16s, and e is another 14, but 16 to the 0 is 1, so that's simply 14 times 1. 14 times 16 is 224, plus another 14 means that the base 10 equivalent of that number is 238. 1000 base 16. Well, be careful with your place value here. That's 16 to the 0, 16 to the first, 16 to the second, and this is 16 to the third. So the expansion here is very short. It's simply 1 times 16 to the third power. That is 1 times 16 to the third, which is 4096 base 10. And our last one. I'm going to start this one above since there's a little bit of room to work. We have a times 16 to the first power plus 4 times 16 to the 0 power. And then we have 0 16 to the negative 1s, 0 16 to the negative 2s, but we do have c 16 to the negative 3s. So what are the equivalent values to that? A times 16 to the 1, that becomes 10 times 16. Plus 4 times 16 to the 0, that's 4 times 1. And c times 16 to the negative third, since c is equivalent to 12, base 10, that's 12 times 1 over 4096. Need a little help from our calculator on that part of a whole here. The whole number part of our hexadecimal number here is 10 times 16 plus 4 times 1. That's 160 plus 4, or 164 point. And c times 16 to the negative third, which is the same as 12 times 1 over 4096, becomes 0.00292969. You can check that on a calculator, and that is the base 10 equivalent of that hexadecimal number. Okay, well, we're going to do more converting into and out of the decimal system from other base systems. And we're going to switch between alternative base systems in the next section. You'll have a Blackboard assignment to go with this. Go ahead and attack that. And as always, be sure to let me know if you need help.